ionization energy. Simply put, it's the amount of energy required to remove, or to get rid of, the outermost electron from an atom/ion. Okay, so the valence electron in a sense. Now, this needs to be in a gaseous state. All right, because in liquids and solids, the adjacent atoms, so you could say this as like the neighboring atoms. Adjacent just means, I guess, just atoms that are beside each other, right? Common vertex side. So the adjacent atoms would interfere in the measurement. So that's enough writing for today. Let's just go straight into the formula. It's better to understand it that way. So we have, let's say, silver here. It's an atom in a gaseous state. It's going to add with something to produce something. The left side here, our reactant side, is going to produce something on our product side. The amount of energy required. Would we have energy on the reactant side, or would we have it on the product side? What do you think? It says the amount of energy required. It's needed. It's not producing energy. That would be here. We're requiring energy, so it'll be on this side. Endothermically, this energy is going to be used to produce something. We obviously know what one of them is. We are removing the outermost electron. The electron is being produced out. It's being gotten rid of. What are we left with? Well, it was our silver that is in question. Our silver lost the electron due to that energy needed. Now it's a little bit more positively charged. It lost just one electron, so it's going to be a 1 plus. Okay, because it has one less electron than it does before, one less negative than it did before. So it is a little bit more positive now. Think of this as an ingredient here on the reactant side, like a chocolate chip cookie, the dough, all the raw ingredients, and then with the energy from the oven, we are now producing a nice, freshly produced cookie. What is also being released in the process? We could say, I don't know, something simple like, the scent, the odor, right? That gets out of the oven and then smells very, very good in the kitchen. So this would be our first ionization energy. You could also have a second ionization energy where you get that product, the one that we made, forgot to put that. So this silver here, you add it with energy, and it's going to do the same thing. It's going to get rid of another electron in its valence shell. So the electron is going to be released again. It released another electron, so now instead of being positive 1, it's now going to be a positive 2. And you can do the same thing for a third, and then a fourth, and then a fifth ionization energy. It doesn't matter. We need to start seeing trends now, like how we saw the trends for the atomic radii. Let's do a few examples. All right. Let's get lithium, for example. All right. And let's say we have sodium. All right. Lithium, 3 protons, 4 neutrons. So there's going to be 3 electrons. 1, 2, and 3. 3 electrons. Sodium has 11 protons, so there'll be 11 electrons. 11 protons. 12 neutrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. Perfect. Okay. Which one do you think is going to be more difficult to get rid of? This last electron. They both have one valence electron. They're both a group 1 element, which means they will lose one electron. And this will be the one on the very last shell, so that's the one that's doing the bond. So how much energy is needed to get rid of it? So what I'm asking is, which element would have the higher IE, also known as ionization energy? Think back to our first, or sorry, I guess our second last video, ionic radii, about the effective nuclear charge. Which one has a higher effective nuclear charge? Definitely sodium, because it has a higher atomic number. Because it has a higher atomic number, because there's 11 protons, and there's a sufficient amount of electrons here, it's going to be very, very tightly held together. Remember, strength comes in numbers. All right? So we would think, it's going to be more difficult to get rid of this electron. However, look over here. Look at this electron. This electron is very, very, very close by to the center of the nucleus. There is only one layer of shielding. This one here has this and this that has a shielding effect. It has an extra layer of shielding. So what we need to look at is shielding effect is having greater precedence over the effective nuclear charge. So this one we would actually think would be more difficult. So our answer would be lithium. All right? Now, this is where exceptions come in. I want to show you two more examples where using shielding isn't necessarily going to be helpful. And we'll have to use what I just talked about, the effective nuclear charge being the precedent. But even with that, there is an exception. Let me show you. Let's look at magnesium. And let's look at aluminum, or aluminium, however you want to write it. All right, magnesium, 12 protons, 12 neutrons, and it's going to have shell here. So we got 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is magnesium, 12 electrons. Do the same thing for aluminum, 13 protons. I believe it would be 14 neutrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So both have the same amount of inner electrons, the ones that are shielding, so we can't use that as precedence of which one should be higher ionization energy. So maybe I'll write this down here. Which one has a higher IE? So it's not the shielding effect that's going to be put in question of the criteria. It would have to be the effective nuclear charge. getting rid of this electron from the outermost orbit versus, let's say, this one. This one here, the aluminum, has an effective nuclear charge that is higher because it has 13 protons. It's a larger atomic number. So we would say maybe aluminum. Okay? Unfortunately, this is incorrect because I want you to look at aufbau principle. Maybe I'll do it in a different color here. This is something you need to memorize. 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f. And then after that, you're going to have to put a 6s up here, and then a 6p, and then a 6d. And then after that, you're going to have to put a 7s below that, then a 7p. Yours might look a little bit different. This is how I've done it, but you don't have to follow it the same way. Really depends how you were taught. I like it this way, just personal preference, no big deal. Just know the order. So what this is doing is, again, aufbau principle. It's just that the subshells need to be filled from the lowest energy level upwards, right? So up here at the lowest energy level, and then we need to go from the top right, from all the way up here to down here, and then it goes to the next energy level strength in increasing order. So it'll be 1s first, then 2s, then 2p, then 3s, then 3p, then 4s, then 3d, etc. All right. Now, I'm going to draw it for both. Magnesium has 12 electrons. We need to draw electrons, okay? But electrons no longer are going to be drawn as a dot. We're going to draw them as a arrow, okay? The arrow is an electron, and a downwards arrow is also an electron. We're not going to get into details of ferro and paramagnetism. That'll be for another video. Just for now, just know them as different types of spins, okay? This is spinning upwards, and this is spinning downwards. We're not in quantum mechanics yet, so we'll get there when we get there. So these electrons are going to be drawn this way. We need 12 electrons. We need to draw 12 of those arrows. First energy level, this is the weakest one. So the magnesium here has one arrow upwards, one arrow downwards. You can only have a maximum of 2 in the subshell. All right? I believe this is the Pauli exclusion principle. So 1s over here. 2s is going to be on top of that because the s's are going to be on this side, then the p's are going to be beside it, and then the d's are going to be beside it, and then the f's are going to be beside it, okay, in columns as such. So we got 1, 2, and then we got the 2s, 3, 4, okay, and Hund's rule always states that you must draw one upwards first, and then downwards, okay? Upwards, then downwards. Here, let me draw it kind of down here so you have more space. Let's have 1s. So each shell needs to be placed first. Okay? And then when you get to the p's can have a maximum of 3. Again, this is just something you have to memorize. Okay? The s's you can have up to 1. The p's you can have up to 3 subshells. The d's you can actually have up to 5, and then the f's you can have up to 7. Again, we'll go more into detail on that when we get to quantum mechanics. All right, so we got 1, 2, 3, 4. All right, and then again, Hund's rule, 5, 6, 7. Okay, each shell needs to be occupied first before you can add that second electron. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, we're not done yet. We need to do a third one, so 3s. Okay, so now we have 2, 4, 6, 8, 10, 12. Now we have 12. All right, now let's do the same thing for aluminum. 1s. Let's just draw them out first. 2s, 2p, and 3s. Okay, so we got 1 electron, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now we're going to do a 3p as well. 13. All right. let's look at our very, very last shell. Well, this is going to be our last one, and this is going to be our last one. Notice how this one doesn't look quite complete. It looks very unbalanced, unstable. So we actually want to get rid of this one. This is our valence electron that we want to get rid of. It's not going to require a lot of energy to get rid of it. Whereas this one here, it's very happy. A maximum of 2 can fill up that shell, and it has. Why does it want to get rid of that electron? It's already quite happy right now. So it doesn't want to do that. So it's going to require a lot of energy to get rid of that one upside down electron, that arrow here. But it's going to be very easy for this one. It wants to get rid of it. So this will be incorrect. Which one has a higher ionization energy? It's going to definitely be magnesium. This is why we don't want to be using the Bohr diagram anymore. All right, I'm going to repeat that again. We're no longer going to be using the Bohr diagram anymore. These cannot stand up to scrutiny or be consistent enough. All right, let's do another example. All right, now let's do another example with phosphorus. And then we'll do sulfur. All right. I'm not going to draw out the Bohr diagram. Just know that we're just going to be doing the aufbau principle right now. So phosphorus, we have 15 protons. So it's going to have 15 electrons. All right. Sulfur, 16. It's right beside it. So 16 protons, 16 electrons. 1s, 2s, 2p, 3s, 3p, 4s. Okay, let's try it. So we need 15 electrons, right? 15 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Oh, you can already kind of see that this is not extremely 100% balanced. It's not extremely stable, but it looks okay. Okay, kind of looking like a very balanced teeter-totter here. All right, let's look at sulfur. 16. By the way, you can actually do it this way as well. This means the same thing, upwards and downwards. 1s, 2s. All right, let me write it up first. Get rid of that 4s, not needed. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. You can already kind of tell this does not look very good. This one here wants to be getting rid of. That's the valence electron. If we get rid of that, how amazing is that going to be? It looks pretty balanced now. Okay, this looks pretty good. I know that there's not 2 electrons in each subshell, but 1 in each is not too bad. This one here, you get rid of that. My goodness, how bad does that look? Unstable, not favorable condition. So, sulfur, we can already kind of tell, is going to have a lower ionization energy. Because, very easy to get rid of this. Not a lot of energy is required to remove that electron from the outermost orbit. Remember, this is your valence electrons. Right? This whole thing here is your valence electrons. This one here is the one that we want to get rid of. All right. Lower IE. This one's going to be higher IE. All right. Now let's do one more example. All right. Is the second ionization energy going to be greater than, less than, or equal to the first ionization energy? Well, let's have a look. Let's look at our formula. Remember, we did this already. All right. This was the first ionization energy. The second ionization energy. Oops. Oh my. Sorry, in a gaseous state. What am I doing? right? Which one is going to be greater? All right, is the second ionization energy here going to be greater than, equal to the first ionization energy? Well, in general, maybe I'll write this here. In general, the second ionization energy is going to be higher than the first. All right? Why is this the case? Because you have less electrons now. Remember, if you have less electrons, this means, remember, the proton number does not change. So less electrons means that they're going to be attracted even better to the center of the nucleus. Because there's less electrons, right? There is, due to less electrons, due to less electron repulsion, there is one less electron, right? So if there's one less electron, they're going to be less repelling. And it's going to be easier to go towards the center of the nucleus. All right? Remember, the same amount of positives exist. The same amount of protons exist in the middle. However, we looked at the previous examples before where that this isn't always the case. We looked at Mg and Al. We looked at phosphorus and sulfur, and how that those groups in particular, because most of those elements within those groups, or those examples I showed you, follow the same suit of characteristic traits, follow the same thing. So it is a lot better to draw it out using the aufbau principle method and see how these stack up to one another. And does it logically make sense? Are they stable? Are they not stable? In regards to, remember these, right? These electron spins. That will give you a more better indicative answer of whether the second ionization energy is going to be higher than the first. Because most of the time, this is the case here. This is the answer that's written textbook-wise. But remember, it can always change depending on how many ionization energies you do. Because it really matters about how stable this shell is. This way, or if it's like this, and we want to get rid of that.